Hi. Now, let's imagine you're in a transit to your office. It is just you in your car reading newspaper, drinking coffee. It feels great, right? Now, for this to happen, we need not only just self-driving cars, but also intelligent transport systems (ITS). I am Ravteja, and today I am going to talk about vehicular networks that use software-defined networking principles to achieve this. Vehicular networks, or Vehicular Ad Hoc Networks (VNets), play a crucial role in intelligent transport systems. Now, let's look at how this presentation is structured. We are going to look into the details of software-defined networking and vehicular networks briefly before we discuss about the current standardizations of vehicular networks. Then, we will investigate some of the software-defined vehicular networks like 5G software-defined vehicular networks and software-defined vehicular networks assisted by mobile edge computing, and more. Finally, we will have a peek at the challenges in software-defined vehicular networks and security in more detail. Now, let's look at software-defined network. The traditional networks have all the functionality of data plane and control plane in a same switch or router. This made it difficult for introducing new policies into a larger network where all the routers have to be reconfigured. And it also made all the intelligent property proprietary, and each company had to make its own every part of the router, like switching fabric, routing software, etc. Software-defined networking overcomes these drawbacks of traditional networking. In software-defined networks, the data plane, which is switching fabric, is separated from the control plane, which is the routing process, and the functions of a router are separated, giving different vendors to excel in different functions of the router. This makes the networks faster as the volume of data flowing through the network increases exponentially. A typical SDN consists of a controller that controls the network flow and switches that does the forwarding. SDNs can be implemented in centralized, hierarchical, and decentralized designs. The centralized controllers will have a global view of the network. The advantages of software-defined networking are they are directly programmable, agile, centrally managed, programmably configured, open standards-based, and vendor-neutral. Because of the flexibility and reliability and troubleshooting, SDNs are perfect choice for vehicular networks. Now, let's look at the basic structure of Vehicular Ad Hoc Network or VNet. VNets are networks based on different sensors that can establish communication with the other nodes or vehicles in transit in a specific region. VNets are created by applying the principles of mobile ad hoc networks (MNets), which are spontaneous creation of a wireless networks for data exchange. A MNet uses multi-hop strategies to improve the range of data to be transmitted. Wireless sensor networks (WSNs) and vehicular ad hoc networks are the most common applications of MNets and can be adopted in multiple ways like traffic control, environmental monitoring, smart building deployments, military applications, and many others. VNets are motivated by the development of intelligent transport systems and wireless access in vehicular environment (WAVE). Intelligent transport system technologies will require two communication possibilities to be implemented: vehicle to vehicle (V2V), vehicle to infrastructure (V2I). Intelligent transport systems and wireless access in vehicle environment aim to reduce traffic congestions and accidents by adding transceivers in the cockpits of vehicles. Also, non-safety applications such as entertainment, internet access, or electronic messages can be offered by these systems. Now, let's look at more detail into mobile ad hoc networks and intelligent VNets. A mobile ad hoc network (MANET), also known as wireless ad hoc network, is a continuously self-configuring infrastructure-less network of mobile devices connected wirelessly. Each device in a mobile ad hoc network is free to move independently in any direction and will therefore change its links to other devices frequently, which is why this has been the perfect network for vehicles. Each must forward traffic unrelated to its own use and therefore be a router. The primary challenge in building a MNet is equipping each device to continuously maintain the information required to properly route traffic. Such networks may operate by themselves or may be connected to a larger internet. They may contain one or more and different transceivers between nodes. This results in a highly dynamic, autonomous topology. Mobile ad hoc networks are a kind of wireless ad hoc network that uses a routable networking environment on top of a link layer ad hoc network. Mobile ad hoc networks consist of a peer-to-peer, self-forming, self-healing network. The growth of laptops and 802.11 or Wi-Fi wireless networking have made MNets a popular research topic. Many academic papers evaluate protocols and their abilities, assuming various degrees of mobility within a bounded space, usually with all nodes within a few hops of each other. Different protocols are then evaluated based on measures such as the packet drop rate, the overhead introduced by the routing protocol, end-to-end packet delays, network throughput, ability to scale, etc. One main advantage to a decentralized network is that they are typically more robust than centralized networks due to the multi-hop fashion in which information is relayed. For example, in the cellular network setting, a drop in coverage occurs if a base station stops working. However, the chance of single point of failure in mobile ad hoc network is reduced significantly since the data can take multiple paths. Since the embedded architecture evolves with time, it has the potential to resolve issues such as isolation or disconnection from the network. Further advantages of mobile ad hoc networks over networks with a fixed topology include flexibility. An ad hoc network can be created anywhere with mobile devices, scalability, where you can easily add more nodes to the network, and lower administration costs, which is no need to build an infrastructure first. With these positives, follow some obvious drawbacks in network performance. With a time-evolving network, it is clear we should expect variations in network performance due to no fixed architecture, which is no fixed connections. Furthermore, since network topology determines interference and thus connectivity, the mobile pattern of devices within the network will impact on network performance, possibly resulting in data having to be resent a lot of times. And finally, allocation of network resources such as power remains unclear. Finally, finding a model that accurately represents human mobility with remaining mathematically traceable remains an open problem due to the large range of factors that influence it. Some typical models used include the random walk, the random waypoint, and Levy flight models. In intelligent vehicular ad hoc networks, InvaNets, Effective measures such as media communication between vehicles can be enabled, as well as methods to track automotive vehicles. For Internet access, mobile IPv6 is widely accepted solution to provide is a widely accepted solution that has been proposed that built upon mobile IPv6 proxy-based architecture selects the optimal communication mode: direct in vehicle, vehicle-vehicle, and vehicle roadside communications, and provides dynamic switching between vehicle-vehicle and vehicle roadside communication mode during a communication session in case that more than one communication mode is simultaneously available. As we have seen the functionality of vehicular ad hoc networks, now let's see the applications of the vehicular ad hoc networks. Vehicular networking applications are classified into the following three categories: active road safety applications, traffic efficiency and management applications, and information applications. Some of those applications are collision warning or avoidance application, in which data transmitted from the roadside unit to a vehicle may warn a driver that it is not safe to enter an intersection. Effective communication between vehicles and the roadside unit can save many lives and prevent injuries. When a vehicle significantly changes its speed, the application allows such information to be shared with neighboring vehicles via broadcast. This way, drivers further behind are notified by an alarm signal, and as a result, potential accident can be avoided. This type of application can lead to a reduction in the average number of collisions by at least 20%. And next, traffic optimization application, in which any vehicle detecting traffic changes can inform neighboring vehicle and the roadside unit of the situation. For example, vehicles could help forewarn of potential congestion by detecting it earlier, that is, noticing high numbers of moving vehicles at reduced speeds, and then relay this information to vehicles approaching the location. This would allow vehicles approaching the congested area ample time to take alternate routes. Violation warning, turn conflict warning, curve warning, lane merging warning, emergency vehicle warning, wrong way driving warning, and etc. Applications in which these services may significantly reduce number of life-critical accidents. In fact, many real-world accidents occur due to the lack of cooperation between drivers. By providing drivers with information regarding common causes of collisions and roadside accidents, such awareness can facilitate increased prevention of accidents. Payment services, in which reducing wait time and avoiding deceleration while passing a toll collection can help increase efficiency and convenience. And finally, location-aware services. This type of application utilizes infotainment and to help drivers attain the information they need, such as locating the nearest gas station, seeking the closest restaurant, or forms of lodging, or simply informing the driver to help arrive at the point of interest. Because safety-related applications involve and directly affect drivers' lives, the security of this category is not only essential but also should be mandatory. Proper operation of these applications should be guaranteed, especially in the presence of a security attack. Life-critical safety application messages must satisfy latency requirements. Such a message is usually a prerequisite for a timely delivery of neighboring vehicles. Non-safety related applications still need to undergo some form of security, but they have less strict latency requirement. Most of the critical messages in vehicular ad hoc networks are broadcast-oriented safety messages that should be delivered as far and as quickly as possible. In addition, these messages must be secure and must not leak personal or identifying information to unauthorized parties. Thus, when we design a security system in Vehicular Ad Hoc Network, we must consider some of the features that are discussed in detail later in this presentation. Now, as we have got basic knowledge on vehicular ad hoc networks and software-defined networks, let us look at standardizations of vehicular ad hoc networks. The major standardizations of vehicular ad hoc networks protocol stack is taking place in the US, in Europe, and in Japan, corresponding to their dominance in the automotive industry. In the US, the IEEE 1609 Wave Protocol Stack builds on IEEE 802.11p stack, operating on 7 reserved channels in the 5.9 GHz frequency band. The Wave Protocol Stack is designed to provide multi-channel operation, security, and lightweight application layer protocols. Within the IEEE Communication Society, there is a technical subcommittee on vehicular networks and telematics applications (VNTA). The charter of this committee is to actively promote technical activities in the field of vehicular networks, vehicle-to-vehicle communications, vehicle-to-roadside unit communications, and vehicle-to-infrastructure communications. Standards, communications-enabled road and vehicle safety, real-time traffic monitoring, intersection management technologies, future telematic applications, and intelligent transport systems-based services. The IEEE Working Group 1609 started specifying the additional layers of the protocol suite. These standards are IEEE 1609.1 Resource Manager, IEEE 1609.2 Security, IEEE 1609.3 Networking, and IEEE 1609.4 Multi-Channel Operation. The combination of IEEE 802.11p and the IEEE 1609 protocol suite is denoted as WAVE. SAE, Society of Automotive Engineers International, which is which in cooperation with IEEE 1609 Group is working on standardizing the message format that can be used by the IEEE 1609 protocols. Various state-of-the-art technologies are later proposed to address various issues in these types of networks. More recently, there have been efforts towards applying software-defined networking concepts to vehicular networks to leverage the flexibility and programmability software-defined networking brings to the table in such dynamic scenarios. The end goal is improving the performance of vehicular ad hoc networks while making them better suited to promote certain services and applications. Furthermore, the ability to reconfigure the network on the fly brought by SDN allows for some interesting use cases in the vehicular scenario. An example of such use case includes adaptive protocol deployment and multiple tenant isolation. In adaptive protocol deployment, the network can select and deploy its routing protocol based on conditions like topology density, for instance. In multiple tenant isolation, it is possible to create slices, much like a virtual local area network (VLAN), which can be useful to lessen a common issue in vehicular networks, the broadcast storm. Now, let us see some of the software-defined vehicular network. First, let's look at hierarchical software-defined vehicular networks. In SDN, communications with the net controller is critical, and it cannot become a single point of failure in the network. In the event the controller becomes unreachable or unresponsive for some reason, It should be possible to recover as quickly as possible to minimize the ill effects of the entire network. Several designs that use SDNs in vehicular networks are present, but the network operates in different modes based on the level of controller the SDN controller exercises over the rest of the network, ranging from total control to no control at all. Whenever connectivity to the SDN controller is lost, the network falls back to operating as it did in regular VNets. The vehicles are going to run traditional routing protocols to find routes around the network. This showed the feasibility of a software-defined VNet, but only tackled the centralized to V2V communication and did so with certain constraints. As the long-term evolution, LTE was used exclusively for the control plane communication. Hierarchical Software-Defined Vehicular Networks (HSDV) has smaller SDN domains through clustering of vehicles to reduce this problem. HSDV uses clustering concepts to create an infrastructure that allows the network to maintain a functional state regardless of central coordination provided by the SDN controller. In these clusters, the cluster head acts as the SDN controller for the domain made up of its members and also takes responsibility for communicating with the primary controller on behalf of its members. Moreover, it creates the structure to meet the quality of service (QoS) parameters that applications or services need with the network status to attempt the user's request. Now, let's look into the architecture of hierarchical software-defined vehicular networks. HDSV divides the whole architecture into three major planes: data plane, control plane, and application plane. The data plane is responsible for the communication process, providing the data traffic flow management. In HDSV, it manages both vehicle-to-vehicle and vehicle-to-interface communication with different networking technologies such as Wi-Fi and LTE. The data and control planes communicates through the southbound API, which in this case is the HDSV protocol. The control plane is responsible for managing data traffic and network intelligence. The control plane in HSDV has two main modules: Service Manager and Forwarding Manager. Service Manager manages service requirements and verifies that quality of service requirements are met. Forwarding Manager is responsible for routing the data and analyzing the network topology. It is composed of three submodules: the Network Status module, which is responsible for mapping the network topology and classifying it either into dense or sparse, as well as detecting disconnections from the controller; and the Vehicle Status module, responsible for managing the vehicle mobility; and the Routing Table module, which is responsible for dealing with network routing information. The application plane is set for vehicular applications and services that interact with the SDN-based system, either providing services or requesting access to the network. Now, let's look at the division of network in hierarchical software-defined vehicular networks. A network that implements HSDV contains two distinct network objects, classified as either a HSDV controller or a HSDV agent. HSDV controller is the main component in HSDV. Similar to the conventional SDN is the controller. The controller is responsible for managing the control plane, effectively dictating the behavior of the system. It is logically centralized and, as mentioned before, represents a potential single point of failure should it become unreachable or unresponsive. And coming to the HSDV agent, that acts as the agent that communicates with the controller in the same fashion an SDN switch in a traditional SDN. It also contains the intelligence necessary to act as a controller itself in particular situations. HSDV agents represent both roadside units RSUs, which in this network include regular RSUs as well as base station BS cell towers, and vehicles. Thus, agents abstract their underlying network communication technology, making their heterogeneity transparent. The HSDV protocol uses a stable clustering technique. This technique assists in maintaining data transmission when the central SDN controller is not reachable and aims to reduce control communication overhead, thus distributing the network control among cluster heads. The domain leaders in the HSDV protocol serve as local SDN controllers for their respective local domains. HSDV also has a two-layer hierarchy in which the members have their leaders as their SDN controller, and the local SDN controllers in turn communicate with the primary controller to receive instructions such as route updates. When a local SDN controller loses connection to the central controller, it assumes the role of the central controller, managing the network in its domain until the main controller re-establishes a secure connection with them. Now, let us look at how a message will be routed in the hierarchical software-defined vehicular networks. The figure 3 illustrates the routing request mechanism. When vehicle X needs to transmit data to vehicle Y, it first verifies whether it has a route to Y. If so, X sends packets to Y using this route. Otherwise, the vehicle verifies if it's a controller. If not, the vehicle sends a request path message to its controller, its cluster head. If the vehicle is a local SDN controller, it selects a set of gateways to which to forward the request path message to find a route to Y. However, the controller may filter this set of gateways to reduce the number of request path messages sent, thus reducing the total control overhead. Gateway selection is based on the distance between the controller and its neighbors. The method for gateway selection is generally described by the following procedure. The controller checks its neighbor routing tables and finds out which domains are reachable from there and through which vehicles. For each of these clusters, the algorithm will select the gateway closest to the controller that reaches the given target SDN domain. Once the controller selects the set of gateways, a filtering to reduce this set may or may not occur. It then forwards the request path message to the selected set of gateways. Simulation results have showed that hierarchical software-defined networks perform better than traditional routing protocols. HSDV has higher delivery rates with lower delays and overhead, allowing for higher network throughput. Now, let us see another software-defined vehicular network that's based on 5G technology. Nowadays, the fifth generation 5G mobile communication systems are being developed by industrial and academic researchers. With the development of millimeter wave, and massive multiple input, multiple output MIMO technologies, the spectrum efficiency and energy efficiency are obviously improved for 5G wireless communications. Considering the drawbacks of IEEE 802.11p networks such as poor scalability, low capacity, and intermittent connectivity, the long-term evolution LTE mobile communication technologies were proposed to support vehicle applications. However, it was found that when LTE communication technologies have been integrated into vehicular networks, the interference has cut down the performance of LTE vehicular networks. To overcome this issue, the multimeter wave transmission technology was proposed to connect users inside vehicles. On the other hand, SDN was proposed as an effective network technology capable of supporting the dynamic nature of vehicular network functions and intelligent applications while lowering operation costs through simplified hardware, software, and management. Based on SDN, a cooperative data scheduling algorithm integrated at roadside units (RSUs) was developed to enhance the data dissemination performance by exploiting the synergy between infrastructure-to-vehicle I2V and vehicle-to-vehicle V2V communications. However, the SDN technology is limited to roadside units (RSUs). When a lot of vehicles are connected to an RSU, the frequent handover problem reduces the performance of SDN. To meet the high performance requirements such as low transmission delay and high throughput, a new architecture of 5G software-defined vehicular networking is necessary. Based on the basic functions and requirements of vehicular networks, an architecture of a 5G software-defined vehicular network integrated with SDN, cloud computing, and fog computing technologies is proposed to form three logistical planes in network architecture, that is, the application plane, the control plane, and the data plane. Based on 5G software vehicular networks, the information is shared among vehicles and users under the control of the fog computing clusters. To support prompt responses from vehicles and users, fog computing clusters are configured at the edge of 5G software-defined vehicular networks. The data plane includes vehicles, base stations, and roadside units. Functions of the data plane are focused on data collection, quantization, and then forwarding the data into the control plane. The control plane includes roadside unit center (RSUCs) and software-defined network controllers (SDNCs). The RSUC is the control center of a fog cell. Considering the quick mobility of vehicles and the massive wireless traffic between the roadside units and vehicles, frequent handover should be avoided for wireless communications between RSU and vehicles. To solve this issue, the fog cell is used for 5G software-defined vehicular networks. A fog cell is composed of vehicles and an RSU. The application plane directly faces different application requirements from users and vehicles. Based on application requirements from users and vehicles, rules and strategies of 5G software-defined vehicular networks are generated by the application plane and forwarded to the control plane. In general, the application plane includes the security service module, the service efficiency module, and the entertainment service module. As discussed before, frequent handover between the roadside units and vehicles is a problem. To avoid frequent handover between the RSUs and vehicles in the fog cell, a gateway vehicle is selected to connect with the RSU, and then other vehicles are connected with the gateway vehicle by a multi-hop relay method. When a gateway vehicle is located in the coverage region of the RSU, the gateway vehicle directly communicates with the RSU. When other vehicles are located in the fog cell, even if these vehicles are not directly covered by the RSU in the fog cell, they will build a multi-hop relay route to connect with the gateway vehicle, and then the gateway vehicle will forward those requests or data to the RSU in the fog cell. When the gateway vehicle departs from the fog cell, a vehicle in the fog cell is handed off to serve as the gateway vehicle. The numerical results show that there is a minimum value for the transmission delay in the fog cell of 5G software-defined vehicular networks. The minimum transmission delay is 0.32, 0.46, and 0.63 milliseconds, corresponding to the transmission distance of 300, 400, and 500 meters, respectively. When the vehicle density is low, the distance among adjacent vehicles is far, and thus the success transmission probability of millimeter wavelengths is low. In this case, increasing the vehicle density will decrease the distance among adjacent vehicles and then increases the success of transmission probability of millimeter wavelengths. Hence, the transmission delay first decreases with the increase of vehicle density. As we've seen the latency issue in 5G software-defined vehicular networks, now let's look at the throughput of the 5G software-defined vehicular networks. The throughput of a fog cell with the adaptive bandwidth allocation scheme is always larger than the throughput of a fog cell with average bandwidth allocation scheme. The reason for this is that the unoccupied bandwidths in the average bandwidth allocation scheme could be utilized in the adaptive bandwidth allocation scheme. When the bandwidth allocation scheme is given, the throughput of a fog cell first increases with the increase in the number of vehicles in a fog cell. When the number of vehicles is larger than 30, the throughput of a fog cell remains the same. The reason is that all available bandwidth in a fog cell has already been allocated for vehicles. Now, let us look at the challenges of the 5G vehicular networks like low delay, frequent handover, high service efficiency issues. Coming to the low delay issues, when pilotless vehicles are deployed for city transport systems, not only traffic information but also road information should be transmitted to the pilotless vehicles by vehicular networks. In general, safety message transmissions have a very low latency, low delay constraint, such as less than 1 millisecond. When there are many relay vehicles for a multi-hop relay vehicular network, the transmission delay of the warning message will be larger than a given threshold. For some extreme cases, the delay issues could cause fatal accidents. How to optimize route solution is still a key technology for 5G vehicular networks. And now, looking at the frequent handover issues, the fog cell is proposed to solve frequent handover between roadside units and vehicles. However, the handover among vehicles is still an issue for the multi-hop relay link in a fog cell. When a lot of vehicles are handed off between adjacent fog cells, the handover will be simultaneously generated for fog cell and the multi-hop relay links. In this case, the complexity of handover is obviously increased for 5G vehicular networks. Moreover, the propagation delay of the warning message needs to be minimized for vehicle handover in 5G vehicular networks. And lastly, the high service efficiency challenges. For future pilotless vehicles, vehicles are not only the transport tools but also entertainment centers for users. Different multimedia services need to be provided by 5G vehicular networks. Hence, a massive wireless traffic is expected to increase for 5G vehicular networks. It is a great challenge to improve the service efficiency for 5G vehicular networks because of the exponential increase of the vehicles that will be there on the roads when these types of intelligent transport systems are implemented. It has been clearly established from the previous slides that a lot of content will be distributed in the vehicular networks. So let us see an effective way of content distribution in vehicular networks. Due to the increase in development of technology and the rise of self-driven cars and intelligent transport systems, the way people wish to spend their time in transit is going to change unexpectedly. People are willing to use the internet ubiquitously even when they are in cars or buses. Drivers are no longer only satisfying the fundamental functions of vehicles like safety and navigation. Now, drivers as well as passengers wish to enjoy the internet more on the road, particularly to subscribe and get infotainment. This leads to the necessity of huge volume content distribution in vehicular networks. In the future, vehicles will likely have two complementary wireless interfaces for data communications: long-range cellular communication and short-range DSRC communication. Cellular networks offer country-wide connectivity and have already been widely used in many low data rate vehicular applications. For example, the GM OnStar system uses cellular technology to link vehicles with a call center. This enables a call center advisor to remotely give driving directions, diagnose mechanical problems on the road, unlock a door if the keys are locked inside, track a stolen vehicle, direct emergency support to the driver's location, and provide other useful services. However, there are some limitations with cellular networks to support large-scale, high data rate content distribution. First, current cellular networks do not support broadcasting or multicasting. Bandwidth-intensive video is delivered through an on-demand unicast model. When many users are simultaneously streaming the same content in a given cell, each user gets his own video stream and consumes his own portion of the cellular capacity. This unicast model and video's intensive bandwidth demands can cause frequent network congestion. Second, the data capacity in a cell is relatively low. Though 4G LTE may provide high data service for single mobile phone or data terminal, and 5G is going to increase it much more, the number of simultaneous users in a cell is still limited to a few hundred. Concurrent access by too many users can cause severe congestion. Third, the initial establishment of cellular connection takes at least several seconds, and the end-to-end latency is relatively high. These will limit their use in most vehicle safety communication applications. Type-based content distribution (TBCD) that uses software-defined networks may satisfy these needs. According to the content type and number of subscribers, type-based content distribution takes different policies. Control broadcast and unicast for the content distribution. The goal of this method is to provide a unified, personalized content delivery model in a vehicular environment, as well as the following features: quick search of desired content, communication reliability, delay tolerance, high scalability, and efficient transmission under limited bandwidth. Now, let us look at the characteristics and working of type-based content distribution. Type-based content distribution method contains the following characteristics: segment-by-segment transmission, loose coupling, scalability, reliability, and security. Let's look at segment-based transmission. There are mainly two segments, from the content server to roadside units and from RSUs to vehicles. The first part can be done by location-based multicast. The server only needs to push the content once, and the software-defined network logic agents on switches will determine the number of copies and the routing paths to specific roadside units based on the locations of subscribers and the number of subscription requests. Looking into loose coupling, because we adopt the publish subscribe pattern, the publisher or server does not need to specify the actual receivers of the content. The subscribers or content receivers are identified by the content subject and locations, particular areas that the vehicles may stay in, which is a kind of subject-based addressing and location-based addressing. And looking into scalability, because each subscriber of the same content service will participate in content distribution, it means that more subscribers, the better efficiency of the method. And looking into reliability, to avoid the broadcast storm, there will be no acknowledgement. Instead, if a subscriber detects it misses a content update, it will send a retransmission request. Example, negative acknowledgement (NACK). Such request can be sent using the cellular link if the vehicle is out of the radio range of a RSU. Then, the SDN logic agent will build an individual connection between the content server and the subscriber through cellular link and transmit the content update. And looking into the most important part, security, all content packets are signed by the authorized publishers. A node will simply drop the unsigned packets or packets signed by unauthorized users. In addition, content messages are encrypted. Subscribers with the same content service may share the same decryption key, which is updated frequently and can be retrieved from security services. Each subscriber reports their locations to the content server periodically because the software-defined network logic agent will forward the content based on these locations. All the subscribers or vehicle nodes and roadside units are assumed to have abilities to store and forward content. Roadside units and the content servers are connected through the wired backbone networks which have high transmission. Subscribers participate in the content distribution in this scenario. A packet of a particular content may go through multi-hops from the content server to a subscriber. To reduce the unnecessary retransmission of the same packet, each time only part of the subscribers retransmit the packet. The broadcast region of two selected subscribers may be highly overlapped, which is a negative for the content spreading. A distance-based weight and broadcast policy can be used to solve this problem. The rebroadcasting subscribers are selected by their own locations objectively but not by the system subjectively. Generally, when a subscriber receives a new update, it will broadcast the update immediately, but the subscriber may receive the same update packet from its neighbors after the broadcast, which makes the network full of redundant copies of same update. To avoid this, each subscriber should wait a time interval after it receives a new update. The subscriber should leave its source as far as possible. The reason is that to minimize the overlap region between the source and the subscriber, the smaller the overlap region is, the faster the update spreading speed is. Moreover, The farther the receiver is, the smaller the probability to receive a same update. In that case, the waiting time interval is short because the neighbors of the subscriber have a bigger chance to receive a new copy of the update. Thus, the waiting time interval should be inversely proportional to the distance from the source. Now, let's look at how type-based content distribution handles the subscribers that are moving at high speeds. In some extreme conditions, there are not any other subscribers or RSUs in the DSRC region of that subscriber for a long time. In that case, the subscriber will connect the server through the cellular link. The detailed procedure is as follows. A subscriber sends a subscription request to the server. Once received the request, the server begins to transmit the content to the subscriber. In addition, the SDN logic agent on the server will check if there is any other subscriber with the same request. If subscriber is in the DSRC region of a roadside unit, it will receive the content immediately. Else, the transmission will start until the subscriber enters in the DSRC region of a roadside unit. If the DSRC link between the subscriber and the roadside unit is broken during the content transmission, which is probably because the subscriber has left the DSRC region of RSU, then the SDN logic agent will cache the transmitted part of the content and try to reconnect to a new roadside unit. When the DSRC connection is recovered, the content is transmitted from the rest part. Based on the direction of the subscriber, the SDN logic agent on the RSU will notify all RSUs that the subscriber may reach next. These roadside units will download the content in advance. Once the subscriber moves into the DSRC region of one of the RSUs, the content transmission is started. The SDN logic agent on RSU1 will check the direction of the vehicle and then notify RSU2 that the vehicle probably will pass by. RSU2 will download the content that the vehicle have not received completely in advance. Once RSU2 detects the reconnection request from the vehicle, the content transmission is started. At the same time, the software-defined network logic agent will notify the subscriber if it has found at least one other subscribers that satisfy the following requirements: request the same content and in the same direction with current subscriber. These subscribers form an interest group. The SDN logic agent on roadside units will split the content into several parts. These parts will be parallel delivered to each of the subscribers in the interest group without duplication. DSRC only has 7 different channels, out of which one channel reserved for safety messages and only 6 channels can be used for private content distribution. In this way, huge volume of media files can be distributed in the network along with the information related to the roadside assistance and vehicular networks. This is how the exponential increase in demand of content in vehicles can be overcome. Now, let us look at another software-defined vehicular network, a software-defined vehicular network that is assisted by mobile edge computing. The automotive industry has experienced advanced transformations due to innovative technologies, but the communication requirements in terms of latency, reliability, and scalability are beyond the capabilities of current 4G or the evolving 5G and VNets. In order to decrease the overall delay and offload the traffic load from the backbone network, the mobile edge computing (MEC) technology is introduced into the architecture. The new network architecture should meet reliability limitation of 10 to the minus 5, end-to-end communication delay less than 10 milliseconds, and minimum data rate of 200 Mbps simultaneously. The key components are data plane and resources, control plane, and SDN controller. The data plane abstracts the underlying network resources such as roadside vehicles, roadside units, base station transceivers, and Ethernet interfaces as SDN switches. These switches comply with unified scheduling, follow the OpenFlow protocol, and forward traffic to the next hop along the path towards the selected destination network according to the control plane logic. The control is transferred from individual switches to the central controller, and the control entity is transferred from communication device to software that is deployed on the mobile edge computing cloud server as a software component that runs on commodity operating system and allows dynamic access and administration. This transformation permits a client to exchange information with the SDN controller during the service lifetime according to changes in client needs or the state of the client's virtual resources. Now, let's look at the functionality and architecture of software-defined vehicular networks associated by mobile edge computing. The open-flow logical switch consists of one or more flow tables and a group table, which perform packet lookups and forwarding. The SDN switch communicates with the controller using a unified interface and dedicated channel named the control channel. The controller can add, update, and delete flow entries in the flow tables either reactively or proactively. The classical SDN model contains an application plane generated by instances of applications. An application represents a client entity that might request services from an SDN controller server, which usually involve data or resource plane exchanges. These visual applications make the network management more flexible. The VNet has big advantages in vehicle-to-vehicle communication before device-to-device technology is practically used, such as ultra-low latency in endpoint-to-endpoint communication in VNet 1 showed in the figure. However, in VNet 3, the limited coverage issue is exposed because of insufficient RSUs. On the contrary, the cellular network has wider coverage, higher bandwidth, and wider spectrum. The wide network, which acts as a backbone network, is used to undertake the high-volume data exchange between the vehicle and the remote data center. Now, as we saw some of the software-defined vehicular networks, let us look into the challenges and security issues of the software-defined vehicular networks and VNets. As discussed before, low latency, frequency handover, and reliability are the other important challenges. Security and predictability are most important challenges that should be handled thoroughly while deploying vehicular networks. It is essential to ensure that life-critical information is not compromised by a security attacker. Due to the nature of open wireless transmission medium used in VNet, there are far too many kinds of attacks. However, These attacks can be classified based on the nature of adversaries. They can also be classified based on their nature, target, and impact, which helps to determine the robustness of our applications to withstand possible attack. Potential attacks include sending bogus information, such as falsifying the vehicle's current information, tracking the location of a vehicle, jamming the channel for denial of service (DOS), and pretending to be another vehicle. Some of the solutions are security hardware, vehicular public key infrastructure, authentication certificate revocation, detection and correction of malicious data. As of security hardware, among the many equipped hardware components in a vehicle, there are two specific hardware components needed to achieve security in a vehicular network. Event Data Recorder (EDR) to track the specific occurrences of a certain event. This can be linked to the black box recorder in an airplane. And tamper-proof devices (TPD) generate data and generate or receive encrypted messages. TPD provides the ability to verify and sign safety messages. A vehicular public key infrastructure (PKI) entails national and state legal registration authorities acting as certificate authority, which issues certified public and private key pairs to each vehicle. A vehicle's private key may be stored in a tamper-proof device that is onboard equipment. If public key infrastructure detects that a vehicle is sending false information, it must be revoked. If it detects a malfunctioning or compromised device, its certificate must be revoked as well. Even though many problems remain unresolved, it is expected that the drivers and passengers benefit significantly from vehicular networks. Vehicular ad hoc networks will not only provide traffic safety and life-saving applications, but also a useful way of communication among the drivers on the road. Vehicular networking is the enabling technology that will support several applications, varying from global internet services and applications up to active road safety applications. We have discussed the fundamentals of the software-defined networks and vehicular ad hoc networks. We have discussed the possible applications and the use cases that could be supported by vehicular networks in the near and long-term future. Then we have discussed about the current standardizations of vehicular networks. Different software-defined networking models have been explained in a detailed manner to get a clear understanding on each of them. We looked at hierarchical software-defined vehicular networks, which aimed at leveraging the flexibility and programmability brought by software-defined networks in vehicular networks toward improving overall system performance in scenarios where there is a connection loss between the vehicles and the primary SDN controller. The hierarchical SDVN uses a clustering technique to create independent local SDN domains. Then we looked at fifth-generation software-defined vehicular networks that integrates fifth-generation mobile communications, cloud computing, and software-defined networking technologies that provide potential solutions for future vehicular networks. Moreover, fog cells are established at the edge of 5G software-defined vehicular networks, which utilize multi-hop relay networks to reduce the frequent handover between the roadside units and vehicles. Then, we learned about software-defined networking-enabled content distribution in vehicular networks that introduce type-based content distribution. This approach supports large-scale and/or bandwidth-intensive content distribution in vehicular networks. Based on the different types of content, this method takes a push-pull pattern and transmit the content. Also, we take different policies based on the number of subscribers to utilize the push and pull pattern more efficiently. Furthermore, this approach includes several innovative features like segment-by-segment transmission, control flooding, subject-based addressing, and location-based, better scalability, reliability, and security. And then we saw a scalable and quick response software-defined vehicular network assisted by mobile edge computing. This software-defined network enabled heterogeneous vehicular network assisted by mobile edge computing can provide desired data rates and reliability in V2X communication simultaneously. This architecture is developed to maintain scalability and rapid responsiveness. In terms of scalability, it has achieved protocol agnostic hardware in the data plane and software-oriented control component in the control plane, which makes the hardware deployment more flexible. And finally, we learned about the challenges in implementing vehicular networks, especially security issues. We discussed several of the features required to build robust security system in vehicular ad hoc networks. To conclude, vehicular ad hoc networks will not only provide road traffic safety and life-saving applications, but also a useful way of communication among drivers on the road. These are the technologies that are inevitable and are going to revolutionize the transport industry. These are references and acknowledgements to the research papers from which the information in this presentation was acquired. Thank you.